all processes, they try to share the location, they try to share the resources, and when they are running for shared resources, this condition can happen. Then we also discussed the remedy for deadlock, that lock try function, but it can also give rise to liveness failure by condition that is called live lock, and it keeps on waiting for the mutex lock without blocking, but still it is not able to or allow for the progress. So this situation is something similar to deadlock, but it's not deadlock. So both are different. So if you get a question, then you should be aware about that live lock is different from deadlock condition. Then there are characteristics that has to be all four condition has to be hold simultaneously for deadlock condition. So mutual exclusion, that only one process at one time is at that time can use a resource. Hold and wait is the process holds at least one resource and waiting for another resource. No preemption is allowed. So the processes, those are the resources, those are held by a particular process, whether it is of low priority, is not preempted. And so that is what happened to the liveness failure when we actually saw that if a mutex lock is held by a lower priority process, then higher priority process has to wait. The remedy to that solution was the priority inversion. While a lower priority process is holding a resource like a mutex lock, then the priority for that particular time would be changed. So as we have seen that over the time, the priorities of the resources can vary and it can be changed by certain commands. We can use nice command to actually see what are the current priorities of a process. So it changes over the time when a process is under execution, usually happen to the user processes. Then we have a circular wait. Circular wait is saying that there exists the n set of waiting processes, and each is waiting. P0 is waiting for the process resource held by P1. P1 is waiting for the resource held by P2, and so on. And Pn is waiting for the resource that is held by P0. So let us suppose we have only two processes and P1 and P2 here. So this holds some resource. It holds some resource. Let us suppose R1, and this is held by it. And P2 has held the R2. And now what is circular wait is basically this process is requesting for R1 and this process is requesting for R2. So these are dashed lines. Let me draw it like this. So this is these are request edges. So the process P1 holds R1 requesting for R2. Process P2 holds R2 requesting for R1. Now this condition creates a deadlock situation. Now when this is allowed, the circular wait is allowed, then the deadlock condition can actually happen. So we started discussion about resource allocation graph, how the resources are allocated and how we can actually visualize the deadlock condition. These are basically graphs, and based on these graphs, we can judge whether there is a cycle existing in the graph or not. So this is kind of a graph theory that you can use to identify cycles in a graph. So if the starting and the ending point is same, that means that a cycle exists within a graph. And this theory is very important for these days. If you want to go into kind of analysis world, then graph theory is very important for you, because if you see the Facebook, even they apply graph theory for doing recommendation. LinkedIn uses graph theory for making recommending new jobs for all of you. So the graph theory is very important. Anyways, coming back to the resource allocation graph with a deadlock, we know if there is a cycle existing between a cycle existing, and then there is a probability that uh, that the deadlock would happen. So we also discussed about if there are only one instance available for each resource, then deadlock is necessary and sufficient condition. But if there are resources has more than one instances, then it may be possible that deadlock would happen. So now this was a condition when there was a cycle, but uh, because there was an additional resource available through given to T4, so whenever this gets free, this could actually break this cycle. So if we have more than one resources for one instance, more than one instances for each resource, then we can say that deadlock may happen. So this was one condition. Then we discussed about how we can prevent the deadlocks. So there were four conditions that we discussed about: that mutual exclusion, if we can relax, hold and wait, if we can relax, no preemption, or if we can relax the circular weight. So we discussed about three conditions. Then we discussed about we cannot relax mutual exclusion because it is not always, not each and every resource is inherently or intrinsically shareable. Let's talk about mutex lock. It is not for sharing. This is exclusive and happens in an atomic manner. So we cannot share each and every resource. So this condition would never hold true, and we cannot make it true. So we should always have a mutual exclusion. Then hold and wait, we discussed about if we want to relax this would actually enable low resource utilization, and starvation is possible. So the starvation is that some processes would keep on waiting for resources to be acquired, while other are just keep running, and this condition is called a starvation condition. No preemption is also not possible. We discussed about how we can do that, but that is also complex. So it is also not a very best solution to allow for preemption of the resources. Then we started discussion about the circular weight. So circular weight is the condition when the one process is waiting for the resource which is held by another process, as we discussed in the previously. So what would happen? Let me draw here somewhere. So we discussed about that R1 is acquired by P1 and R2 is acquired by P2. Oh, sorry, P2. R2 is acquired by P2. So this is, it has acquired this. So these are resources are assigned now. They make request for this resource and it made a request for this resource. So now these are basically the request edges. I can make it like this. Now this condition gives a deadlock situation. I hope you agree that if this is a condition, if I allocate any one resource, let us suppose, then it can create a deadlock situation for us. Now, this can create a deadlock situation, but this was allowed. So if we can impose some terms onto this particular thing, then we can avoid the deadlock condition and we can prevent the deadlock. Now, how that happens, let's discuss that. So let us suppose if we, this is happening because the resources are able to capture each other's resources and waiting for it. Now, for that, what is given that each resource is assigned an integer number. So R1, R2, so each one would be assigned an integer number. Now, if a resource, if a thread initially requests a resource Ri, let us suppose R1 here. After that, a thread can request only in the instance Rj only if Rj, the integer number of Rj is greater than the integer number of R1. So it can, that thread, if it has already acquired R1, which has integer number 1, then it can request only R2, which has integer number 2. So it can only request for a resource which is higher in the integer numbering, so which is numerically higher than the previous one. In this case, what would happen if this is allowed? Then let's consider the case of P2. Now P2 is already allocated R2. P2 is already allocated R2. So it cannot request next for R1 because the number 1 here is smaller than 2. So in this case, P2 would never request for R2. So this would never happen. If this link is this would never happen, then we can say and we can see that the cycle would never be created. And if there is no cycle, there is a relaxation of deadlock. So deadlock would not happen in this case. So I hope you got a sense of how the ordering which is given to the resources would break this circular weight, and that would basically prevent the deadlock condition. For deadlock condition, we had for deadlock to happen, we had 4 conditions, and out of the 3, we were not able to relax, but we can enforce some numbering mechanism on 2 resources so that the circular weight would never happen. And if this circular weight is broken, this condition is broken, then we can prevent the deadlock. So alternatively, we can say that a resource Ri must be released. Let us suppose if P2 want to use R1, then it must release R2 before using it. This is the terminology and the enforcement of this particular decision onto any process which want to use. Let us suppose if P2 want to use R1, it has to release this resource R2, and this would break our circular weight. So using this protocol, the circular weight condition cannot hold. So let us the threads involved in the circular weight at T0, T1, Tn. Ti is waiting for a source Ri, which is held by T1 plus 1, Ti plus 1, and Ti plus 1 is holding the resource Ri while requesting for Ri plus 1. So this condition is saying that this must be true for all, that the resource which it is requesting, the thread which it is requesting for a resource should be of higher number of the integer which is given. Now giving integer number to a resource is dependent upon the application developer, or so that is how you are basically assigning that number. So that would break the circular condition. Why? Because if we say that Tn is waiting for a resource which is held by T0. Okay, so in this way, by transitivity, so f R0 is smaller than R1, Rn smaller than next, and then this would make this is smaller than R0. So this condition means that R0 is smaller than R0 itself, which is impossible, and that's why there is no circular weight happening. So just to simplify what I said, I think example makes it more clear and more sense that any resource numbers are allotted to the resources, and each resource can request for a resource with each thread can request for a resource which is higher in number rather than lower number. If it requires to requires a lower number resource, then it has to release all other resources. So that condition would actually help us to break the circular wait. Now, the second part is deadlock avoidance. In deadlock avoidance, we need to know some information about the resources. We need to know how many resources a process requires before it start execution. So if there are two resources and P will request R1 and R2, then we know that who would be using how many resources and what are those resources. In that case, we know that this situation could lead to a deadlock condition, so we can avoid that deadlock condition. So deadlock avoidance is different from your deadlock prevention, because in prevention we try to fail one of the condition. In deadlock avoidance, we need some extra information about the thread which is running and how many resources it is going to use. So based on that, we make a calculation that which resource is allocated to which resource. We will shortly see when we are doing the question. Deadlock algorithm dynamically examine the resource allocation state to ensure there can never be a circular wait condition. And resource allocation state is defined by, so this is important, resource allocation state is defined by the number of available, allocated, and maximum demand of the process. So we say that we visit the state of the process, and based on the state, we actually make the judgment whether this could lead to a deadlock condition or not. For Linux, give us a lock depth tool, which is not available for production environment. If you want to test, you need to enable lock depth feature by going to edit config file through menu config, and then you have to recompile the kernel, boot a new kernel image, and then you will see under proc folder, you will see the folders related to lock depth. It basically enables, it's a monitoring tool which monitor the mutex and how they are allocated, and when they are allocated, and if there is any deadlock condition, then it would actually notify you that these processes could lead to a deadlock condition. This is used for testing purposes. If you are developing some application and you want to see that that if your application could lead to a deadlock situation, then you can use this deadlock lock depth tool. There are many other tools, but this is one of the tools that is available for Linux. So I was discussing about the deadlock avoidance. So deadlock avoidance would always try to have a safe state. Now, what is safe state? It is basically creating the sequence of threads so that they always run without interfering with others, and the sequence, the way they are running, should be satisfied with the resources which are available. So if a safe state is, if let us suppose there is a sequence. Now what this sequence means, that the threads would be running like T1, T2, so on. So this is an execution path. So T1 would be allocated the resources it requires, then T2 would be allocated the resources it requires, and so on. When T1 executes it, so now is that if a process or thread gets all the resources it requires, then it will complete its execution and run it. If a thread waits on a particular resource, it goes to the waiting state. This we have already discussed. Now, if T1 got all the resources, it will execute it and release all the resources. Then those resources can be given to T2. It will execute it and perform its function and releases all resources. Then those resources would also become available. So what is safe state? If that for each TI, the resource request that TI can still make can be satisfied by currently available resources plus resources held by Tj. So what are Tj? So let us suppose I talk about T2, T3, Tj here. So I'm talking about that this, let us suppose this is Ti. So these all are Tj set. Let us suppose this all is a set. So in this case, what it means that Ti's request can still be satisfied if all the threads before it can run, and they once they run, they execute, they will release the resources, and these resources would be available for Ti to happen. So I mean to say that if there is an ordering in the sequence, like at any position Ti, it could still be satisfied by the resources which are released by the previous resources threads, and also the available threads. So in this situation, if the resource Ti needs not to be immediately available, Ti can wait, and all Ti have been finished. So the safe state is that the sequence, the ordering creates a safe state, and the available resources can actually meet the expectation of that sequence. So this is called safe state. If no such sequence exists, then the system state is said to be unsafe. Remember that if there is no sequence that is available, then your system is in under unsafe condition. Now we shortly going to discuss about that. So let me show you what I mean to say. So this is an example that is there. So let us suppose we have three threads, T0, T1, T2, and each requires some number of resources to be executed. Okay. Now, if this is the sequence, this is the need of the threads, and we have a total thread equals to 12. So we have 12 resources; those are available. And this is the maximum need of each resource. Now, the safe sequence would be that each would be assigned a slot in the set, the sequence, so that all threads can run and justify and satisfy the need of each other. Okay, so if we run this like T4, T1, then T0, then T2, this makes a safe sequence because this sequence would actually satisfy the need of each and every thread, and they would never be waiting for the other resources which are held by the previous thread. So this means that a sequence, how they would be executing, now that should be safe. It means that the sequence would have numbering, how the threads would be running, and a higher order, the T2 here, would be satisfied by available resources plus the resources those are held by T1. So this is the meaning of safe sequence. Now, if our sequence is safe, then our system is deadlock free. If our sequence is unsafe, means there is no sequence available, then there may be a condition that deadlock would happen. So you're very clear, if you can make a safe sequence, then you are deadlock free, you are avoiding deadlock. If you're not able to create a safe sequence, the sequence is unsafe, then it can go for deadlock. Okay, so now this is the same thing that we discussed. Now there are two avoidance algorithms or approaches. One is using the resource allocation graph, and other is Banker's algorithm. We are going to discuss shortly, but before that, I would like to discuss on safe sequence. So let's see how this happens. Let us suppose in our system, I have 12 resources and 3 threads are running at an instance T0. Each thread would have certain requirement for the resources. Let us suppose T0 requires 10 resources to actually get executed. Once the 10 resources are available, it will complete its execution. T1 needs 4 resources, T2 needs 9 resources. Now, out of this, at time T0, 5 resources are allocated to T0, 2 resources are already allocated to T1, and 2 resources are already allocated to T2. So whenever a question would come, you will be given this particular matrix. This would be given to you. Now, the maximum resources those are available would also be given to you. So what you need to add is how much is the need now. So need is the max need minus allocation. So the max and the need is max need 10 minus what is allocated. So it requires 5 more resources to get executed. Then we have for T1, the need is 2 because 4 minus 2 is equals to 2. For T2, the need is 9 minus 2 is equals to 7. So this number, the maximum number that a thread can expect from the system is 12. So this should never be more than 12, because if the system do not have more than 12 resources, the thread should not ask it. So this is also a condition that has to be checked for whenever a thread is having a maximum need. If some thread is requesting more than the resources which are available in that particular system, it would never execute because the resources would never be available for that. Okay, now allocated are 5 plus 2 plus 2, it is 9. So there are 3 available. So let us make this table. This you have to create. This table has to be created. Now let's see the safe sequence. T1, T0 requires 5 resources to get executed, but at time at any snapshot, small T0, the available resources are 3. So 5 are required for T0, but 3 are available. So what would T0 do if there are resources which are not available for a thread? Then what our thread should do? Either it start running or it keep waiting. What should be it doing? T0 should wait. So this would wait. So T0 would wait, and in this condition, T0 is waiting. We move to T1. Now the requirement of T1 is 2. We have available 3. So resources can be allocated to it. So if the resources are allocated to this thread, it will complete its execution. So once it is allocated, this thread would be eliminated from the queue. Okay, if it is eliminated, it will free the allocated resources. And what would be the new available here? The new available would be available plus the allocated. So 3 plus 2 is equals to 5. Now new available resources is 5 because T1 has already executed, and this would be made available for T0. Now T0 needs 5 resources, 5 are available, so T0 would also execute. So once the resources are available for a thread, imagine an idle condition, all are available, it will run in microseconds and complete its execution and free all the resources. So once this is done, what would be the new value of the available? So 5 is this value and allocate. So 5 plus 5 is equals to 10. Now new available resources are 10, and we have left with T0. So T0 is going to be executing because it needs 7. So it executes. Once it executes, the available resources would be 10 plus the allocate, so 12. So all 12 resources which we started initially are now free. after executing these this way. So T1, T0 and T2 is a safe sequence. It means that now you might have understood what I was saying, that the T2, the need of the T2 was satisfied by the available resources, and the resources those would be released by T0 and T1. So this made a sequence T0, T1, T0, T2 a safe sequence. At any time snapshot, let's suppose any time snapshot T0. This is the condition. T0 was added to the queue. It required maximum number of resources 10. Then T1 is added. Then T2 is added. So 10, 4 and 9 are there. As they added into, they requested different resources. T0 requested for 5, T1 requested for 2, and T2 requested for uh, 2, uh, 2 resources. So these were the request. Those are made by the processes, and they were allocated at this particular time. So once this is the snapshot, now we want to move ahead from this. We want to move from time T0, okay? The maximum need, the exactly how many more are needed for this thread to get executed? 5. T1 requires 2 and T2 requires 7. So this you need to calculate. This would be given to you. The maximum need and allocated would be given to you, and the number of threads and resources available would be given to you. Now you have to calculate how many is needed. How many are needed for this process or thread? So 5 are needed, 2 are needed, 7 are needed. Okay. Let us suppose at time T1, it requires 5 resources. It tries for all 5. It requests for all 5. Okay. In that case, what would happen? It requires 5 and available are 3. So what it would be, it would do, if the resources are not available for a thread while it is executing, then it must wait. So T1, T0 start waiting. It goes into wait state. Okay, so if this goes into wait state, what would happen? T1 would come up. T1 requires these many 2 resources, and how many are available? 3. So 3 would be allocated, 2 would be allocated from 3. Now in that case, available would become 1. Okay, so we can go that way also. So these are allocated to this. Now this become 4. Okay, now once it become 4, maximum need and allocated become same. This will execute. This is deleted. Once this is completed, all 4 would come back here. So 1 plus 4. So I did in a different way. What I did is, the formula which would be more consistent with is that available I, so next available I is equals to available 3 plus allocate. So allocate is 2 plus 2. Okay, so this is the formula. This might be a little confusing, but this is the formula. So what we are doing here is available, whatever was available. Once this is executed, all the resources are released. Whatever is allocated would also be released. So 3 plus 2 is equals to 5. I hope the 5 was actually required by T0. So now allocate, these are allocated here. So it becomes 5 plus 5, 10. So when need becomes equal to allocate, this will also execute, and it will release all the allocated ones also. So what would be new available? Available I minus 1, it is 5 plus allocate. So what was allocate here? 5. 5 plus 5 is equals to 10. Okay. This is another way of doing the same thing basically. So if we first allocate, then all are released. So this is coming back here. Okay. Now it has 10. It requires T2 requires 7. So what it was done? We allocate it, 7. Now this is become equal to this. So it will also execute and return back us. So 10 plus 2 is equals to actually, return back all the resources. So 12, we started with 12 and we got back 12 resources. I hope now this is clear. Now, let us say that the system made another request. So it can go from a safe state to unsafe state. So suppose that at time T1, thread T2 made a request for one more resource. So thread T2 made another request. So now allocated a 3 to it. So it was previously 2. So now it is 3. So if we have allocated 5 plus 2 plus 3, so we allocated 10 and we have total available, total are 12. So how many are available? Equal to 2. So these are available. And what is the need here? 10 minus 5, 5, 4 minus 2, 2, 9 minus 3 is equal to 6. Okay. Now we have to create a safe sequence. Let us see whether we are able to create a safe sequence or not. Now 2 are there, 2 resources are available. T0 wants 5 resources, 2 are available, so it is waiting. T1 requires 2 resources, 2 are available, so allocated. Okay, T1 would execute. So once this would execute, the new available would be 2 plus coming from here and this 2 coming from allocate. So it becomes 4. Okay. Now 4 is the total number of resources which are available. And what would happen? 4 are available. T0 requires 5 and T2 requires 4. Now we have one resource smaller than what are actually required. So this would keep on waiting and T2 would also keep on waiting. This has already gone. Now what is this condition? T0 and T1, T0 and T2 both are waiting for the resources, but there are fewer number of resources. Then this would make our system to go into deadlock, resulting in a deadlock. And our mistake in granting our request to T2, just one resource more, lead our system from a safe state to unsafe state. So only T1 could execute, but neither of T0 or T2 are just stalled. So they are just waiting. Okay. So this is because they are waiting. They cannot make any progress. There is no safe sequence existing. Given the concept of safe state, we can define that avoidance algorithm can ensure system would never go into deadlock. So if they are into unsafe state, there may be a deadlock. If there may be a deadlock, because deadlock is the condition that one has held the resource that is needed by another. It could be the deadlock, but there's no safe sequence existing in the previous example. Okay. So whenever a thread requests a resource, it is currently available. The system must decide whether a resource can be allocated immediately or the thread must wait. So the system should check before allocating a resource to T2 whether the state would remain safe or it become unsafe. If the allocation of one resource to T2 remained a safe sequence, then it would be allocated. If it converts it into unsafe state, then that resource allocation would not happen and T2 should actually wait. This is what is the meaning of safe state. The request is granted only if the system is in the safe state. What happens? Okay, we do the calculation. Okay, so let us suppose somebody asked me to give me some money. Okay, if you have an extra money, I would do the calculation. Does this, if I give X amount of money to somebody, does that creates an unsafe condition for me or not? if it does not create unsafe condition for me, I'll allocate, I will give the money. Okay, otherwise I will not give that money. So this is just pretending. The system would pretend, try to check for the future. If I allocate this, what would be the next state of the system, whether it is going to be safe or unsafe, and based on that, it make a decision right now in the point whether to allocate it or not. So that is called a safety algorithm. So whenever there is a request for the new resource allocation, the system would run safety algorithm by just pretending that it has allocated some resource and then do the calculation. If that brings in that the system would lead into unsafe condition, then it would not do that allocation in actual way. So that is basically the safety algorithm. We will discuss more on it. Now, can you fill in the need and available and the safe sequence? Can you guys create it? Need is 3, 2, 4. Available are 9, 12, 3. Okay, can you guys create a safe sequence? Everyone should try it, because this is the base for the next what we are going to discuss, and that is more complex. So please, everyone tries. We have 3 available. T0 require 3, so it will be allocated, and this allocation would lead to the new available would be 3 plus 3, 6. It requires 2, 6 would be allocated, and 2 will be allocated out of it. So this will execute, this will execute. Once this will execute, allocate plus this become 11, and allocated now need, it requires 4, so 4 are allocated. So this would be, once this is done, there would be 11 plus 4 is equal to 15. So we started with 15 resources, and once all are executed, we got this is equals to 15. So T0, T1, T2 is also a safe sequence. T1, T0, T2 is also a safe sequence. Okay, so both are safe sequences. Now, if the safe sequence is existing, it means that our system would never go for deadlock condition. Okay. Now there is the variation for that we can use source allocation graph scheme to identify the cycles. So it says that it adds to the previous allocation graph where we have 2 edges. One is assignment and another is request edge. Here another edge is added that is called claim edge. That indicates that the thread Ti may request the resource Rj in some time in future. So if this happens, if there is a claim edge, we know that this could be a request in the future, and based on that we can make a judgment that whether a cycle would exist or not. So coming to example directly, so here we can see this is T1, this is T2. Now these are claim edges, and this is a request edge, and this is assignment edge. So resource T2, resource R1 is allocated to T2. Sorry, resource R1 is allocated to T1, and resource T2, thread T2 is requesting for R1. So resource R1 is allocated to T1, whereas T2 is requesting for it. Okay, and then we have another resource R2. But here we have 2 claim edges. These are claim edges. So claim edge says that why claim edge is added, because T2 may require this resource in the future. Okay. Now let us suppose the condition that T2 requests R2. T2 requests R2. It has changed that to basically a request edge. This has been changed. Now this has become a request edge. Although R2 is currently free, this is free because this is not allocated to either of these, but it would not be allocated to T2. Why? Because the graph, the claim edge says if we allocate this to anyone here to here, it could create a cycle for us. It could create a cycle for us. If this goes like this, if this goes like this, we allocate R2 to T2, and then this somewhere in a next future time started claiming this, started requesting this. So if this is the condition, do you think there is a cycle condition? So basically that's a futuristic thing. We try to look into the future, whether there is a condition that could lead to a cycle. So if I come back to what I was saying, okay, now we can see that these are two claim edges. If we allocate R2 to T2, it will become this as an assignment edge. Now here T2 has acquired R2 and waiting for R1. T1 has R1 and in the future it started requesting for it. Now this would create and lead to a cycle condition, and this is a deadlock condition. This is good when we have only one instance for each resource, and this would actually help us to identify the cycle. So unsafe state in resource allocation graph. So this is unsafe state, and we never put our the resources and the threads into unsafe state. That could lead to a deadlock condition. So this would be not allocated. This would never happen because this could lead to an unsafe state for the processes or the threads which are currently running. So this is how we can use a resource allocation graph by adding another edge called claim edge to identify the cycle in future and then not allocating the resources. Now next is the Banker algorithm. Banker algorithm is very important and used in banks to actually allocate the total amount available in the bank to end customers. So it becomes as a resource and a request problem. So it can apply to multiple instances. When a new thread enters the system, it must declare the maximum number of instances of each resource type that it may need. So whenever a process enters, it has to declare the resources it requires. The number of resources should not exceed the total number of resources in the system. When a user requests a set of resources, system must determine whether the allocation of these resources will leave the system in a safe state or not. So before allocation, as we discussed in the safe state, before making any allocation, system would run, the Banker algorithm will call safety algorithm, and based on the safety algorithm, it would check if it leads to the safe state or not. If the sequence is safe, then allocation would be performed. The only thing added here is multiple instances for the resources. If the resources are allocated, otherwise thread must wait until some other thread releases enough resources. So this would happen if our system is or the sequence is not safe. Now for Banker algorithm, there are 4 data structure that has to be managed. One is available array. Available array is a vector of length m, where m is the number of resources which are available. If something is, it requires basically how many instances are required for a resource rj. So k, it will hold that value. Then we have n is a max matrix, which is n into m. So n is the number of threads those are running, and m is the number of resources. Each would have different instances. So max ij equal to k, then it means that the process ti may request at most k instances of resource rj. So if it is max ij means equal to k, if this is holding this value k, then it may request that ti would request at max k instances of that resource type rj. So whenever a process enters into the system, it has to give this information to the algorithm. Then is an allocation. This allocation is another matrix. So allocation ij equal to k. It means that Ti is currently allocated k instances of Rj. So available, what are available resources as we discuss in the safe state? Max, how many are the maximum required for that particular thread for a particular resource? And allocation is how many are actually allocated. Then we have need matrix. So need matrix is also how many are needed for that thread to run to the execution. So the max minus allocated is equals to need. So need comes with this formula. Okay. And these data structure vary over time, both in size and value. So because there would be more threads added over the time. Let x and y be the vector of length n. Then if this is the condition, like x require these many resources and y require these many resources, then we can say y is less than equal to x condition. So this we may be using. We treat each row in the matrix as allocation I and need I. So allocation I is a array for thread Ti in allocation, and need I is again it represents the need for the thread I. So there shouldn't be any confusion about it. Now the safety algorithm, how it runs, this is a pseudocode of it. So it says it initializes two vectors of length L, M and N. M is number of resources, N is number of threads. So for work is equals to available. Now work is at any instance of time, let us suppose T0. This safety algorithm is going to run. So work is equals to available. Whatever is available, if three are available, like the matrix is available like this. Okay, now this is allocated to work. This is the initial condition for work. Then finish I is equals to false for all n. So for all the threads, it is made n. Whenever the safety algorithm is going to run, find index I such that both finish I is equals to false and need is less than work. So we try to find that index now. It will try to find out whether it is T0, T1, T2, for which thread we are talking about, where this condition is true, because initially finish is, false. So this would be true for the first iteration, and it will look for the need is less than work. Now, what is work? It is basically available in the initial condition. Okay. So if the need is less than work, then go here. It means that if the need is less than work, we allocated to that particular thread, and work become equals to work plus allocation. So which is this formula. So here available is equal to available plus allocate. So there it become equals to, the work become equal to work plus allocation, and finish I is equals to true. We made it true, and then go back to the condition true, look for others which are there. If this whole loop would run, and at the end finish I is equal to true for all I, it means that system is in a safe state. Now, because there may be more than one instances available, so let us suppose A has 10 instances. Now this is the condition. There are 5 processes. Process and thread are used interchangeably, so do not confuse. So P0 through P4, there are, so this should be T0, this should be T4. So there are T0, T1, T2, T3, and T4 there are 5 processes. Each has a max need. So T0 requires 7 instances of A type. T0 requires 5 instances of B type. T0 required 3 instances of C type. Is this clear? Okay, now this is the max need required for each type of thread. And now we make, let us suppose this is given to us only. This will be given to us. So we have allocated 0, 1, 0 out of the max need 753. Okay, so what is the need for it? How much is the need? So 3, 4, and then 7. This is the need here. Okay, now for this, what is the need? It is 2, 2, 1. What is the need here? Here it is, the need is 0, 0, and then 6. The need here is 1, 1, 0, and need here is 1, 3, 4. Okay, so now this is the matrix. Okay, so 7, 4, 7, 7, 4, 3, 1, 1, 1, 2, 2, 6, 0, 0, 0, 1, 1, 4, 3, 1. So now let's see, available are 3, 3, 2. From how we calculated this? We calculated by this. Add this 0, 0, 2 plus 1 plus 2, 5. So we have 7 instances, so 2 are pending. 1 plus 2 out of 5, 3 are pending. So available. So 2 plus 4, 5, 3, 5, 7. So out of 10, 3 are 7. So this is how we calculated available. Now this is at snapshot of T0. Okay. Now we have to create a safe sequence. What would happen? If 3, 3, 3, 2 are available, which can we run this? 7, 5, it requires 7, 4, 3. We have available 3, 3, 3. So T1 is waiting. Sorry, T0 is waiting. Now we allocate this to here to T1. So 1, 2, 2 is there. Okay, so once it is available, it would be executed. Now what would be the new available? It will be allocated plus available. So 2, 3, and now it is 5. So 5, 3, 2 is available. Correct? Now the same thing is happening here. So once we have this available, which one could run? Can we run this T2? Can we run T0? No. Can we run T3? Yes, we can run. So it will be executed next. This will be executed next. And what would be the new available? So this plus this. So it will be 3, 4, and 7. So 3, 4, 7 would become the new available. Now, can we execute T0? Yes. So once we go for here, so what we executed here is T1, T3, and then T0. We go to T0. So this would actually free us this money. So it will be the new one would be 7, 5, 3 after execution of T0. Now 7, 5, 3 are there. Which can we next allocate? So we can run T2. So 7, 5, 3 is allocated to this. Now T2 is executing. Now what would be the new available? So it will add this to this, add this to this. So it is 10, 5, and 5. So what once T2 also executed, how many are there? So it is 10, 5, 5. Now this is the new available. We can run T4. So once T4 is executed, what would be our final resource available? T10, 5, and 7. And this is what we started with 10, 5, and 7. Okay, can you do this thing? Can you calculate this? Let us suppose at time T1, thread T1 made a request 102. Okay. Now this is a new request that is coming to the system, to the previous state. Now what would happen? Now we have to run the safety algorithm. Okay. So safety algorithm pretends by accepting that request. So it will accept that request. What it will do is it will change the values for that particular thread. So earlier the allocated was 200. Now the allocated has 30. So now the allocated is this. We need to calculate the need. New need would be different. So here the need was 1, 2, 2. Now here the need would be, 0, 2, 2. And the available would also be smaller. So now the available has become 2, 3, 0. Okay. So now can you come up with some sequence? Can you do the calculation? Is it a safe sequence or not? Is it a safe sequence or not? Yes, it is basically still it is still a safety basically sequence is available. It could be different the way we are calculating, but if the safe sequence is there, the demand is, any thread requirement is satisfied by any sequence, that becomes a safe sequence. Okay. So can you check for, let us suppose once this state is there, can you check for this particular request 020 added by T0? So what would be the process? So process would be the safety sequence would try to accept it as and pretend it that it has been granted. Then it will check for the safety sequence. And if the safety sequence says this sequence is safe, then this allocation would be actually done. Otherwise, this will not be allocated. Now, coming back to the algorithm. So here you can see the safety algorithm. What it does is it creates a work, temporary variable work and finish. It pretends that the matrix has been like that, already allocated. So try to find out need less than work. Okay, make it true and then allocate it and update the value of finish. So this particular loop would actually, look for the safe sequence. If all finish are true, then our safe state is safe. Otherwise, our state is not safe, or sequence is not safe. And in that case, the allocation would not be completed.